Welcome to our discussion on modeling with exponential functions. We're going to look at a few specific uses for exponential functions. And that is because there are a lot of processes that occur in the natural world that follow an exponential growth or an exponential decay, i.e., they can be modeled very accurately with exponential models. So let's start with doubling time, which is a growth, right? It's doubling. And you've seen probably riddles and parables about this. You know, the guy will put a grain of rice on each square of a chessboard and so on and so forth, and it doubles and doubles and doubles. Well, anything that keeps doubling after a given amount of time can be modeled with a very simple function that's just 2 to the t, where t is the amount of time it takes for something to double. So for instance, if we start with 10 bacteria, then that's our initial amount, and then that is going to be multiplied by 2 to the t because that 10 is now going to double, right? We're not starting with 1 and then going to 2, we're starting with 10. So in one set of doubling, it goes from 10 to 10 times 2 is 20, right? Where t would be 1, meaning one kind of doubling amount of time. So in this case, it's slow growing bacteria and it takes 3 hours to grow, and we're going to let t be in hours. So that's why it's t over 3, because you have to put in a 3 for t, and that creates your first doubling, right? If it was just t on its own, then when t was 3, it would be 2 cubed, which would be 8, and it would go up by a factor of 8. So you always have to take your t and divide by the doubling time. That's where this little a comes from, right? Your doubling time. You also have to pay attention to what is your degree of measurement, right? Are you measuring in minutes and hours and days and years and eons or whatever, right? So you got to make sure that you're in the right unit of measure. So now, under ideal conditions, we have a bacteria population doubles every 3 hours, as we saw. Now we're going to say there are 1,000 bacteria initially, and we want to find a model to tell us what this population is going to be after any amount of time, t hours. We want to find out how many bacteria we're going to have in exactly 15 hours, and then we want to solve backwards and figure out how long it's going to take until we have 100,000 bacteria. So the first one's really simple. We already know that our doubling time exponential growth formula is always going to be our initial amount. So in this case, 1,000 times 2 raised to the t over a, where a is the amount of time it takes to double. And in this case, we said it was 3 hours. So that's why we get 2 to the t over 3. So after 15 hours, we just put 15 in for 3. I'm sorry, 15 in for t. We divide by 3, which gives us 5. We raise 2 to the 5th, which is 32, and then 32 times 1,000, so that's what we get 32,000. So we can see that we get 32,000 bacteria after 15 hours. We want to figure out how long it takes to get to 100,000. Well, we know it's going to be at least more than 15, right? Because that only got us to 32. So we just set our output, right? Our n of t to be that 100,000. We still got the same function, right? 1,000 times 2 to the t over 3. And now we need to solve for t. That takes a teeny bit of algebra. The first thing we want to do is divide both sides by 1,000 so that we can kind of, see, we're trying to solve for t, so we need to kind of peel all those layers away from t. So the first thing we can peel off is that 1,000 times. So we divide both sides by 1,000, and now we've got 100 equals 2 to the t over 3. Now that t is trapped up there as a power, and we need to solve for t, so we need to undo that layer. We need to undo the layer of the exponential, and the inverse of the exponential is the log function. So you take the log or natural log, right? You can take a log of any base, it doesn't matter. Since we're dealing with tens, right? 100 is a power of 10. Taking the log of both sides will leave us with nice, pretty numbers, because log is, by definition, base 10. But anyhow, you can do this in your calculator very easily to figure out what log of 100 is, what natural log of 100 is. Doesn't matter. You do the same thing on both sides. You either take log of both or natural log of both. But the nice thing about taking any kind of logarithm is the power comes down in front and becomes multiplication. So now it's just t over 3 times the log of the base. So there's my log of 2. Like I said, we could do this in the calculator. It ends up being 2 because it's asking the question, what power of 10 do we have to get an answer of 100? And obviously 10 squared is 100, so that's where we get the 2 here. Again, we want to solve for t, so we need to undo all of these remaining layers. So the first thing I would do is I'd multiply both sides by 3 to bring this over here, right? And get 6 equals t log 2. Then divide by log 2, and there's how we get t is 6 over log 2, which gives us 19.93, or roughly 20 hours. Okay, so that's doubling time. What about if we have just a relative growth rate? So we've used this exponential function with a base 2 to model growth in terms of doubling time, but we could also do the same thing if we wanted to figure out what it was in terms of tripling time, which would be a base 3. And in fact, we can do this with any base we want. Base 2, base 3, base 7, base 2.5, anything except for base 1, because base 1 doesn't make sense, because as you raise it to a powers, it never changes, right? It's always 1. You also obviously couldn't do base of any negative numbers or 0. So any positive number can be our base except for 1. Okay, so if we use the base e, and e is a special number, it's a what we call an irrational number. It's kind of like pi, where the numbers just keep going on and on forever and they never repeat. Then if we use that e, we get a population model in terms of what's called the relative growth rate, r, which is the rate of the population growth that is expressed as kind of a proportion or percentage of the population at any time. So if we say something is growing at a 2% growth rate, right, or a 10% growth rate, that's going to be our R. So in this case, right, if we're using E, then R is what's considered our instantaneous growth rate. And don't worry about what that means. It just means that we're kind of using it as that same idea of doubling time, but now instead it's just a percentage. So as I said, we could do 10%, 2%, whatever we want. Whatever we do, the percentage always has to be listed as a decimal. So if we're going to say the growth rate is 2%, then R is going to be 0.02. Really, anytime you deal with percentages in any kind of formula, you're always going to list the percentage as its decimal equivalent, right? You're never going to put 25 with a percent symbol into a formula. You would always have to do 0.25. But in any case, here is now the more generic exponential growth function. You'll see that we still have this n sub 0, which just means our initial population size, just like we had in our previous doubling time formula. But instead of 2 raised to a power, and in that power was specifically t over a, right, our doubling time, well, now we're taking this and we're generalizing it to a growth rate, and it just becomes e raised to a power. And in this case, that power is r times t, our growth rate times time. And remember, the r just always has to be expressed as a decimal. So you can see how the two functions are very, very similar. Now, the same principle is at work in both of these functions. That's why they look so similar. A population of 1 million, for instance, will increase more in 1 year than a population of 1,000, right? Because the more you have, the faster it grows. So we can figure out this same idea of the bacteria growth, but instead of knowing what the doubling time is, we just need to know how fast it's growing relative to itself, right? What's its growth rate as a percentage? In this case, we're going to start with 500 bacteria, and it's going to grow at 40% per hour. And now we can find a function. We can figure out how much there is after 10 hours. We can figure out how many hours it takes to get to 80,000. And we can even sketch a graph using technology, really. So here's our function, right? Just like before, here's our initial amount, but in this case, that's 500. We knew that it was growing at 40%, so it's e to the rt. There's our r of 0.4. If we want to know how much we have after 10 hours, we just plug in our 10 for our t, stick this in our calculator, and round to the nearest whole thing, because you can't have a percentage of something, right? You can't have a fraction of a bacteria, so you get 27,300. We can solve backwards just like before, right? And set our total population to 80,000 with the 500, with the e to the r to the times t. We're solving for t just like before. We divide by the initial amount, which gives us the 1600. Now before we did logs because our numbers were powers of 10. Now that we're dealing with e, we want to take natural logs of both sides. Again, it will work if you do any log. This just makes the math easier. So you take natural log of both sides. This is just going to be natural log of 160. The nice thing of natural log of e to some stuff is, just like before, the stuff comes down and then it's times natural log of e. But the reason why we do natural log is the inverse of e. So when you take natural log of e, you just get 1. They undo each other. It's like squaring a square root. So that's how we get from here to here, is that natural log of e to some stuff just becomes the stuff. And now it's really easy because you just divide by the 0.4, and there's our t. Slap that into your calculator and get 12.68, or roughly 12.7 hours, or you could even say roughly 13 hours. And then if you wanted to graph it, that's what it would look like. Again, you're going to need technology to do these types of graphs. Okay, next look at radioactive decay. Instead of things growing and doubling and all that kind of stuff, radioactive decay is something that's kind of dissolving. It's going away, right? It's dying off. It's decaying. And we talk about, instead of a doubling time, we talk about a half-life. How long does it take for this substance to lose half of its substance, right? To lose half of its mass or half of its volume, however you want to think about it, but basically to shrink to half of its size. So some examples are, we know the half-life of radium 226 is 1,600 years. So if you started with 100 grams, you would have 50 grams, or half of that, 1,600 years later, right? A long, long time. And then another 1,600 years, it would go in a half again, which would leave us with only 25 grams, i.e. 25% of 1/4 of what we started with, right? So you're basically multiplying something by a half at a given interval of time. So here's the formula. We have that same initial amount, right? Only now we're just calling it m sub 0, because instead of a number of things, we have a mass. Big deal. It's the same thing as the other formula, right? It's just a silly letter that means something. In this case, it means the same thing, an initial amount. Now we're back to that 2 raised to a power, but instead of t over a, where a was the amount of time it took to double, we have negative t over h. Again, h is the same thing as a. It's just now we're normally talking about radioactive decay in hours, so that's why it's an h. But the unit could be anything, really, right? And then t, again, is what was before, time, and now we just have the negative in front of it because it's going away, right? Negative, it's going down, it's decaying. So that's how you can kind of remember which formula to use. Now we can simplify this by using e when we have a relative function, right? So we use this one when we know what the doubling time is. So if they tell us, hey, or sorry, if we know what the half-life time is, if they tell us, okay, it takes 1,600 years for half-time, great. Then we use this formula, we plug 1,600 in for h. If we don't have that and they tell us that it's just decaying at a rate of 10% per hour or 10% per day or whatever it is, but it gives you a percentage, then we use the ER version, right? The E and the R, where the R would be 10% or 0.1. The negative is still there, right? So here's these two formulas. You can see they're very similar. Again, we use the 2 when we have a time, an actual half-life time, and we use the E1 when we're given a percentage increase or decrease. Okay, so we could solve for R in this formula and figure out what our kind of half-life is by setting up the function of how long is it going to take for our initial amount to be our initial amount divided by 2, i.e. how long is it going to take to be cut in half. we would divide both sides by the m sub 0, the initial amount. So that's where we get 1/2. So now we're saying, okay, e to the negative rh is how long it takes to go to a half. Take a natural log of both sides. Remember, the e goes away and we just have the stuff. Then we divide by h, and we can see that you're probably asking, where did the negative come from? Remember, the negative just makes it get smaller. We're just solving for its rate, and we always talk about a rate as a positive amount, right? It has a decay of 10%. We would just say 10%. It's technically negative 10% because it's decay, but we just make it positive because it's easier to talk about. So this is how we could solve for r and figure out what our r was if we were just given the half-life stuff. So here's our simple model. We can always use this one where r equals natural log of 2 over h if they gave us just the half-life time, right? So if they tell us it's half-life every blank, you could put that in for h, and then you could always use this formula, so you don't have to worry about having two formulas. But this one's pretty darn easy to remember or put in your notes, so you could always use both. In any case, here's an example. Polonium-210, half-life 140 days. Suppose that we start with 300 grams. We can find a function with the 2 in it. We can find a function with the e in it. We can find the mass remaining after 1 year, and then we can do this whole solving backwards thing again and figure out how long it's going to take to only have 200 milligrams of it if we start with 300. Well, here's the 300, right, in both formulas. That's our initial amount. They told us the half-life was 140, so in this function with the 2, we just put the 140 in here. In the e function, we remember that our r is going to be the natural log of 2 over the h that they gave us. So we have to stick that in the calculator, and we get this approximation. So there's our r. So there's our two functions. These two are exactly the same, right? Now we can plug in 1 year. Now remember, t, if we go back here, right? T was days, right? Took 140 days. So our time is in days. So if we want to know how long it's going to, what's going to happen in a year, we don't put a 1 in there. We put a 365 in there because that's how many days we have in a year. So when we put that 365 in, and again, stick it into a calculator, we get that we'd have about 49 milligrams left. If we used the e function and we wanted to solve for how long it takes, then we've got the 300, the e with its stuff, set equal to 200, right? It's for our original function, our original amount, and all that kind of stuff. And then we do some simple algebra. We would divide both sides by the 300, right? Divide by the 300 to get the e all by itself, and that's where you get the 2/3. Then take the natural log of both sides, because that undoes the e, and we just get the stuff, this negative blah, blah, blah t, natural log of 2/3. And then to solve for t, we divide both sides by this negative. Now, of course, you could do natural log of 2/3 in your calculator, and you can get a number, right? Then you could write that down, and so on and so forth. But just remember that if you're doing intermediate steps and you're writing down numbers, you have to keep a lot of decimals, because if you want your final answer to be accurate to, let's say, 4 decimal places, you always have to keep at least 2 extra. So if you did natural log of 2/3 in your calculator, you would have to keep 6 decimals. Write that number down, then divide it by the 0.00495, and then take that final number and round it to 4 decimals. So just keep a lot of extra decimals if you are having trouble kind of doing this stuff, quote unquote, algebraically, and then plugging this all in at the end, because you could just do natural log of 2/3 in your calculator and then say divide by 0.00495 and hit enter, and then your calculator keeps all the decimals possible, right? So it keeps a lot more decimals. It becomes more accurate. But in any case, it takes roughly 82 days. And that's what it would look like, again, if we use some technology to graph it. Okay, our last example, Newton's law of cooling. It's a really cool law, no pun intended, that tells us how fast it will take for an object to come to the temperature of its ambient environment. So the rate at which an object is cooling is proportional to the temperature difference between the object and its surroundings, right? So if you have a really hot object and you stick it in really cold surroundings, there's a huge difference between those two. It's going to cool much quicker than something that you put in a warmer, like say for instance you had a hot cup of coffee, you stuck it in the refrigerator, it's going to cool slowly. If you stick it in the freezer, it's going to cool even faster. Kind of makes sense, right? It's kind of intuitive that it should do that. But in any case, here's the formula, write it down, put it in your notes, and then just tell yourself what all of these things are. So the temperature of the surroundings, T of S, right? Temperature of surroundings. D sub 0, remember anything sub 0 is initial. In this case, it's the initial temperature difference between the objects. So it's the difference between the object and its surroundings. And then we've got that same old E. We've got T for time, and we've got K, where K is a positive constant that depends on the type of object we have. So we'll always be given that in all of our examples. So you can see that it's very similar to the radioactive decay where we had negative RT, but here we have negative KT. Same thing as R. K, same thing as R, it's just a number. We're just going to have, because it's a constant, that we call it a K, but I know constant starts with a C, but anyhow. Same idea. So for instance, cup of coffee, heated to 200 degrees Fahrenheit, placed in a room, has a temperature of 70 degrees. After 10 minutes, the temperature of the coffee is 150. So find a function that models the temperature of the coffee at T, find the temperature of the coffee after 15 minutes, how long will it take to cool to 100, and then we can draw a graph, right? So these are all the different things we'd be asked to, and you might be saying, hey, where's our K? Well, because they gave us a temperature after a certain time, we can solve for K. So plug in everything we know. Here's our room temperature, right? They told us the room was 70 degrees. So there's my room temperature. Just remind yourselves, right? Here's the surrounding temperature plus the difference, e to the kt. Well, we plug in all of those bits and pieces. In fact, let's bring that function back in to remind ourselves, just so we can see where all these bits and pieces come from. So TS, right, 70. The difference is 200 minus 70, so there's our 130. And then e to the negative kt. So here's our standard function for this cooling coffee. Now we can use that to solve for K based on the two pieces of information they give us. They give us its temperature, right? That's the output. So this number here. They tell us the time, how long it took, and you can see the only thing left in this would be K, the only thing unknown. So we plug in everything they tell us. It cooled to a temperature of 150 in 10 minutes. So there's our 10 for T and our 150 for the temperature. Now all we got to do is a little math, right? Subtract 70 to make this 80. Divide by 130. Again, we're trying to solve for K, so we're peeling all those layers off. We get 80 over 130, which reduces to 8 over 13. Now we've got this e to some stuff, right? So what are we going to do next? That's right. We're going to take a natural log of both sides. The natural log gets the stuff down, right? So instead of e to the negative 10k, it just becomes negative 10k. Natural log of 8/13. Divide both sides by negative 10. In this case, we're just showing it as multiplying by negative 1 over 10, but you just put this whole thing divided by 10. Doesn't matter. But anyway, you got to put it in your calculator, and you're going to get 0.0485, blah, 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 round at 55. That becomes our k. We now can put that back into our function with our surrounding temperature, our difference between the two temperatures. Here's our K. And now we can solve everything as before. We can figure out what the temperature is after 15 minutes by putting that into our function as our T. Remember, we're going to have to use some technology. We can solve backwards, right, by figuring out how long it's going to take to get to a temperature of 100 by putting in 100 for our answer. And now instead of solving for K, we're solving for T, right? Before they told us the time and we solved for K. Now we have the K and we're solving for T. So you can see how it's going to be the exact same process we did before. Plug everything in, solve for what we don't. So the first thing we can do is move the 70 over. So there's our 30. Then we're going to, then we divide by the 130. We take the natural log of both sides. divide by that number, slap it all in our calculator, and about roughly 30 minutes or about a half an hour. And then if we wanted to graph it, stick it in some technology of your choice, and there's our decay. You can see it's just like the decay function, the cooling function, right? The temperature is going down. And that's all I've got.